Sorry for the delay in getting here. All right, give everybody a second to start showing up. I thought I had things set up so that you guys had, no, I guess not for this one. Okay. So I am in the middle of also working on an IEP information stuff for so I'll be back. You'll see me actually, but I'll be back. I'm going to try this. Let's see. Can I'm going to turn off my video for a second and I'll be right back. Okay. Okay, back to this. Boom, boom. Let me put my, here we go, boom, and boom. There we go. So Ivan, you there?
Yeah.
Hey, how you doing?
I'm good.
Let's see. Why do you think Alex is texting me? Hold on. What is the link to the help session? It's on school. Jeez, hold on. Now I got to go get the link and send it to him because apparently he can't go to school. But all right, courses, AP Physics, links for class meetings and help sessions. Period 7 help session. Copy. All right, Alex, hold on. He probably tried to come on right at the beginning, and I took a while to end up my help session, my fake office hours, and nobody shows up to because I don't want him to anyway, so it's fine. Oh, there he is. I see the top of your head, Alex.
Yeah.
Yeah, it's nice. Oh, there you are. Hey, how you doing? Good to see you. Yeah, I have office hours, I guess. Yeah, from 12 to 12:30, just largely for any of my intro to engineering kids that need help with something. Of course, I haven't met with any of them yet, so. And I let that run past because I was working on something for the special ed department.
Oh.
So, you know what's great is my background is actually Rouge Ahmed's house. She sent me a picture of her. I said, I like that. And so we're going to start exchanging houses. So if you want to send me a picture of your place, I'll be in your house next week. Isn't that awesome? How creepy is that? So I'm going to go back to where I feel most at home. There we go. So you have questions, Alex?
Yeah, it's just like.
All right. Let me pull up the stuff in question, and we'll start looking at them. Are they with the multiple choice mostly?
Yeah.
All right. Let me go get them. I can't do this. Sorry, struggling with it. We're gonna say I want. All right. I have two sets of. I think this working. All right, this is okay. So here we go. Working energy, multiple choice questions. Yeah, here, there. All right. So which ones you worried about there, my man?
How would you do number 4?
4? Which one?
Mm-hmm.
The working energy 1 or 2?
1.
1. All right. All right, let's do this. Boom. All right, you can see my screen now, right?
Yeah.
All right, rubber ball with a mass track. The ball. Go away. The ball bounces off the floor, and during the bounce, 0.6 joules of energy is dissipated. We assume that means to heat. What is the maximum height? All right, so how much energy does it have? All right, we're going to attempt this. Ready? No. So there you go. So you have it up here, and then it falls down, it hits the ground. Here's the ground. And then it bounces back up. That's not going to bounce up as high because it lost some of this energy here, dissipated into heat. So what I need to know is how much energy did it have at the start when I let it go? Did you calculate that?
Yeah, it would just be what? It's mass times height, right? Or is it mass mgh?
MGH, right? So we can figure out its height, its energy here, its initial energy. Okay, so let's do that. I got a calculator here. Hold on. There we go. Boom. Okay, so I got 1.5 meters is height times a mass of 0.2 kilograms times 10. All right, conveniently enough, it's 3, right? So it's got 3 joules of potential energy here. When it bounces back up to this height, how much energy is it going to have?
0.4 of that energy.
Well, it says it loses 0.6 joules. So we have 3, and I lost 0.6. So that should leave me with a new energy of 2.4. Yes, joules?
Okay, yeah.
All right, now, from that, that's the new potential energy. I keep the same mass, the same G. I just have to solve for the new height. Now, right? Just acknowledge that you know how to do it now. Okay, good. Because we don't necessarily need to figure out, go through and do the calculation to see. You could probably set up a proportion and do it quicker, but I'm okay with this. So we have an initial energy. After the bounce, it lost 0.6, so it only has this much energy, so it's not going to go as high. And take that new energy, set it in the same equation, but you're just going to solve for a new height.
Okay.
Now, let's see. And I would anticipate, we look at the answers, 1.5, it didn't lose that much energy. So, in fact, you could look at it like this. It lost, what is it? Point now here. Don't gasp, Wellborn. You'll just embarrass yourself. So it lost 20% of its energy. So since everything's linear here, I would assume it lost 20% of its height, which is going to be 10% is 1.5. So it should be like 1.2 meters, maybe.
Yeah.
All right. It's safe to play that little percentage game because everything in this equation is linear. If it was the kinetic energy, if we're comparing those, I'd be very careful because of the squared. Ivan, if you have a question, feel free to speak up. Otherwise, we know Alex is going to dominate things. Look at him.
I don't have any questions.
All right. So you're good. And just then, Alex, what else you got? I'm going to start recording this session. I guess it's already being recorded. Interesting. Okay. No?
What equation did they use for number 5?
Oh, so what, number 5? What?
Yeah.
Okay, so they teach you this in driver's ed. Have you finished driver's ed yet, either one of you?
Yeah.
All right.
Yeah.
They taught you this in driver's ed. I don't even need to teach you this. They don't explain why. Well, I'll show you why in a second. But if you double your speed, you quadruple your stopping distance. If you triple your speed, your stopping distance is going to go up by a factor of 9, 3 squared. See, and it all has to do with the fact that velocity gets squared in the kinetic energy. So if you have, so the distance is going to be x, but here's why. So let's look at it this way. So if you initially are going at a certain kinetic energy, so kinetic energy, oh boy, I'm working on it. So would just be 1/2 mass of your car, velocity of your car squared. No big deal. And when you go to stop, that's going to be equal to the work done by your brakes, by friction, which is going to be the friction by your brakes times the distance it takes you to stop. Well, this right here, you can't change. There's a maximum. When you hit your brakes as hard as you can, that's the best force you have. You can't get any better. So this is really a constant. If you're going faster and you have more kinetic energy and you're going to use the same force, it's going to take you longer distances to stop. This makes sense.
That makes sense.
Now,
Yeah.
the issue is that by doubling the velocity, because of the squared, that factor of 2 gets squared, it becomes 4. So in the second case, the kinetic energy in the second case here would be still 1/2, still mass, but this would be 2v squared, which is going to produce a 4. So you're going to have 4 times the kinetic energy. Using the same force to remove that energy, it's going to take you 4 times the distance. And now he's looking out the window.
No, I was thinking.
This is why people, Ivan's like, this is why I don't put my video on, so that Wellborn can't be like, what are you doing? You over there. All right. So yeah. So what if I stop? What if I went 5 times as fast?
Then it'd be 25.
All right. So it's all down to the square there. And it actually is a good, like, it's the thing they really should teach in driver's ed, because kids think the difference between 20 miles per hour and 40 miles per hour, 40 is still slow. But if it takes you 30 feet to stop at 20, it's going to take you, 120. It's going to take you 120 feet at 40 miles an hour. Like, the distance you're going to require to stop is going to go way up. And kids don't realize that. All right. Ooh.
Why is 6 speed decreasing instead of acceleration is negative?
Yeah, because you could have a positive acceleration and still be decreasing your speed.
Like, hold on.
Right?
Yeah.
So I now I don't see an example of that here, but you could be like, the line could be going like this. That's an example of a positive acceleration that decreases a negative velocity. So it's, technicalities. So cart is constrained to move along a line of varying force. What is this a graph of anyway? Velocity?
Yeah.
All right. So yeah, anytime that the speed is decreasing. So even, all right, ready? So even here, with the example I did, if you had this, oh, come on, Wellborn. Oh, we'll do a line. Hold on. I got this. If you had this as a segment on there, it would be, this actually would be negative work as well, because the displacement would be in the negative direction because it's moving in the negative direction, but your acceleration is positive. And so those are in opposite directions. The force is opposite the direction of the velocity, so you're slowing down. The key here is that the work done, the net work done on something, will always show up as a change in the object's kinetic energy. And kinetic energy doesn't care about direction. So if your kinetic energy decreases, it's negative. Doesn't matter what direction. If your kinetic energy increases, it's positive. So this is going faster, it's an increase. Here is an increase in kinetic energy. Doesn't matter that it's in the negative direction, kinetic energy doesn't care.
So for number 7, you'd find the area under the curve, right?
Yes, that's an old one. Velocity, the area under curve, velocity versus distance versus time is a, yeah. So you're just going to kind of count the blocks in each section. Looks to me like this would be the winner. I would think. I mean, just by counting them, 1, 2, 3, 4, 5, 6, 7, almost 8. Actually, combine it. So it's like 8 or 9. This is 1, 2, 3, 4, 5, 6, 7, 8. This is less than that. This is, yeah. So I'm guessing AB would be my answer on that one. All right. Are we just going through them in order, for God's sakes? I mean, you guys are welcome to work on them, and if you get, I don't have to talk the whole time. If you guys just want to, yell or I guess in Ivan's case, I don't know what you would do, Ivan, if you mute yourself, but I guess you have to unmute yourself and speak. But if you get stuck on something, but there's no point in me just, you know, unless I see one in here that I really like. Curious. Interesting. Yeah, you know, actually, this one right here, what is this, number 12? Try number 12. It's got an interesting twist to it, I think, if you haven't already. You know what I'm going to do, Alex?
What?
I'm going to go make popcorn. Yeah. All right. Oh, I'm going to see. Let's see. Yeah, let's go. I think I'm going to go do that. So just yell. I'll be over here making popcorn. I'm not in my room, right? I'm at home, but. See that, Alex? That's a bin of popcorn. That's popcorn. All of that. It's popcorn. You listen carefully. A couple minutes, you might hear the sound of it popping. All right. So, how's it going so far? Do you have the change in kinetic energy?
That's what I was finding.
Nah, good. Find the change in kinetic energy and we'll go from there. Actually, I think 13 is an easier, unless I'm missing something. You know what? Hold on. All right, there's a couple ways you could get at 12, I think. Interesting. So you could do 12 with kinematics, I think, and F equals ma. It's one possibility. It's a couple others.
Wait, so what did you do once you have the change in kinetic energy?
That's what makes this one tricky, because change in kinetic energy, which is no big deal. It's 1/2 m, which is the same, obviously. 1/2 3 times 5 squared minus, well, yeah, I guess the other way around. 1/2 3 times 3 squared minus 1/2, the same thing with 5 squared. That's going to equal to the work done by the net work done, which is the work done by friction in this case, which is the force of friction. The issue is, this is why this is an interesting problem. This is the force of friction, but I don't know the distance. I know the time it takes to get through there. I don't know the distance. But this is where I think a little little kinematics would help us. Probably the best way to, the acceleration here is going to be constant throughout. So one quick way to get through this would be to say, probably the easiest way to get through this would be this. What's the average velocity during this stretch?
4.
All right, so it comes at 5, leaves at 3. Literally, since it's a constant deceleration, the average velocity is 4. All right. If you move at an average velocity of 4 meters per second for half a second, how far did you travel?
2 meters.
2 meters. So what we know is, this is an arrow, is that our distance covered is now, we know is 2 meters. It's a little bit of a dip in a different direction to find it, but it is. So now I take that change in kinetic energy divided by the distance it travels, which is 2 meters, and that should give me the force. The change in kinetic energy is technically negative, but they just want magnitude. So what I find interesting here is 13, we've already found the answer. When we found the change in kinetic energy, that is the answer to 13, isn't it?
I think so.
Right? It should just be the change in kinetic energy.
Mm-hmm.
You could do this one right here, straight up with kinematics. Can you hear the popcorn?
Yeah.
Good.
How'd you do with kinematics?
I would, let's see. You would know initial position, we'd call it 0. You know initial velocity, 5. Don't know acceleration, so maybe I wouldn't be able to. Well, yeah, I can do this. My final position I don't know. But I do know my final velocity, which is 3, and I know the time. Yeah, it's just 0.5 seconds. So I want an equation that doesn't use position. So that's going to be V equals AT plus V original, right?
Well,
Yeah.
Yeah. I just shut the popcorn maker off, didn't want it to burn. So I could find acceleration from that, correct?
yeah.
Yep. So I could find acceleration, and then I would just use net force equals ma, and the only force in town is going to be friction. So I just take that acceleration times the mass, and that should give me the force. So that is the other option, a combination of kinematics and Newton's second law. We used average velocity to find distance, and then use that. So they're probably about as equally as complicated. It's just, what's interesting is one of those cases where the second question in the series is actually something, if you use our method, you'd have already found.
Wait, so when you get the acceleration, what would you do next?
I just multiply it times the mass, right? Net force equals ma.
Mm-hmm.
And there's only one force in town in this case, it's friction.
And then negatives wouldn't matter because it's magnitude.
Right, exactly. Yeah, just whatever on the negatives, not worry about that. I'll grab that. Don't panic. I know you can't smell with this, but man, you should smell the popcorn. That's not something I want Zoom to incorporate. Hell of everybody's houses. Good Lord, no. So can you hear me when I'm walking around the apartment here? Is it? That's kind of nice. Just like in class. I had to heat up the topping, the buttery fake topping. Yes. Oh, wait till you wait. If we ever return to school again, Alex, you're going to be so happy. I actually found the product that they use in movie theaters.
Yeah,
And I mean,
isn't it like mostly soybean oil?
oh yeah, it's soybean oil and enough and carcinogens, but who cares? It tastes good. All right. What's a little carcinogens between friends? All right. Yeah, I'll bring that in. You got to heat it up to make it really good. So it's on the stove right now, heating up. All right. Oh, this one just looks. It's got springs and incline. Are you kidding me? You can tell I don't read the questions before I assign them. Wow. This is a fun one right here. Why don't we see if we can figure this one out? An object of mass m on a spring, so it's released, and it goes down to here. Is that what I'm reading? Yeah, the object is released from rest in the spring. All right, so it's released here, and it stretches to here. Ooh. Yeah, let's try this one. I'm assuming there's more than one question. No, just this one. All right. What's the magnitude of the work done by gravity as the object slides down the plane? Huh? Huh.
Can we look at number 9 after that one?
Yeah. A couple ways to look at this, really. All gravity cares about is the up and down, doesn't it?
Yeah.
So a couple ways to look at this. One way is to say this is the only this is actually the distance that matters for gravity. This vertical drop, because anything horizontal is perpendicular to the force of gravity and doesn't count. So really what I need is this distance here. Well, if x is the hypotenuse, I hope you can tell what I'm writing there, right? If this is x and this is theta, how would we find this side? SOHCAHTOA. So if this is theta here.
Opposite, it'd be sine of theta.
All right, so opposite and hypotenuse. So the sine of theta is equal to the distance I want. I'm going to call it x vertical. X vertical. No, let's just call it D. Just call it D. Oh, I can do this. I have an eraser. Yeah. And I'll just call this distance D. There we go. That was so much better. Over x. And so now what about the force of gravity on the object? Don't overthink it.
10.
Well, now the force is mg, right? All right, so just mg.
Oh, yeah, mg.
Maybe I should have called it h, but so in this case, the force that gravity does is from here is downward, and it's equal to the weight, because that's what gravity pulls, and the vertical distance it moves is x times sine theta. That's when I solve this for D. That's what I get. I swear that's a D. There we go. So the work done should be mg times x sine theta. Is that one of my choices? There we go. I'm guessing this one would be right.
Can you explain that one more time?
All right. So I need here. Let's draw it this way. No. Hold on. Oh, there we go. Okay, I guess I don't get that. I'll use this. So this is the distance x. This, come on. This is one feature about this I'm not crazy about. There we go. This is the vertical distance that it moves. And in fact, I'm going to change that color to like blue or something, because that's, can we change it to blue? No? It's not going to let me change it to blue. Nah, the hell with it. All right. Doesn't matter. Now this one's going to be blue. Watch this. You son of a bitch. See, if I get too close to one of them, it makes me, yeah, it's annoying, but that's okay. There we go. So this right here is x, the distance it moves down the ramp. But gravity, the only displacement that matters for gravity is this distance here, the vertical one. That's why I call it D. I guess I could have called it H, but that's all right. So I know that the work done by gravity is going to be the force of gravity times the distance perpendicular, or sorry, the distance along that it moves along the same direction as the force. So it's going to be this distance, meaning that. It's going to be the part that's vertical. Because the fact that it moves left and right means nothing as far as work is concerned for gravity. And so the real question is, what is this distance? How can I describe this distance in terms of x and theta, which is why we did the whole trig thing. So the work done by gravity is going to be the force of gravity, which is just mg, times, and this distance here turns out to be opposite. It turns out to be x times the sine of theta from SOHCAHTOA. Cool. Now that's just one way to do it. Here, you want another crazy way to do it? Ready? Let's see. All right, what the object moves from here to here. What part of what's the force of gravity along this direction, parallel to the thing? Do you remember what that is?
Like the equation for it.
Well, it's not really. Yeah, there's an equation for it. It's not like in the equation sheet.
It's
But
like
it's going to be the let's see,
sine of theta.
sine. So mg parallel to the ramp is mg
Would be
sine theta. Now, in this case, we're looking at it from a different perspective. We're looking at it as this is the amount of force that the part of gravity that pulls down the ramp. What's the distance it travels down the ramp?
the height of the ramp.
No, not the height. In this case, we're looking at it from this as the perspective of this. So it's just x. So in other words, I can keep gravity whole, right?
Mm-hmm.
And find only the vertical distance it travels, or I can break gravity up, so mg, so into the part of gravity that pulls along the ramp. So then I break, this is the piece of gravity that moves the object down the ramp, times the whole distance of the ramp, which is x. So there are two subtly different ways of looking at this. This one is looking at the full force of gravity over only the vertical distance. This is the full distance down the ramp with only the part of the force that pulls in that parallel direction. But they turn out to be the same thing.
Okay.
So there's two ways you could really approach that. I don't know if mine's better or not. Let's see. Well, what the heck? We're on this last one. Let's look at it. Here, read it and look at it while I finalize my popcorn making. Oh. You guys see that they posted the date for the AP exam?
No.
All right, so they thought I posted it somewhere or I sent a link around or something. All right. But here, it is. So it's going to be the 14th of May at 4 p.m. is the first session. There'll be a makeup session on June 2nd at 2 p.m. Don't ask me how to access it yet. I'm sure we'll figure it out eventually. Are both you guys signed up to take the exam?
Yeah.
So yeah, it's that's all I know at this point is the testing windows. We'll have to make sure that between now and then they're supposed to give us practice exams and so that we get used to like how the server is going to work and all that. But that's our target date at this point, the 14th. If you really want the extra time, we could probably ask our counselor to push it back. The only danger there is that if we have technical difficulties, you lose the opportunity. We can determine that in a little bit. So AP gave us the whopping extension of like a week. But they did cut the exam down, I guess, so. All right.
Wait, so the exam's only a short answer?
Right, it's only free response. They're supposed to give us info on what the types of questions they're going to ask as well. So.
Is it how many free responses is it going to be?
Good question. It's going to be less, I think, than it has been in the past. I'm guessing 2 questions, maybe 3, but I don't know for sure yet. Or at least I should know, I guess, but I can't remember what it said. But I do believe it won't be more than 3 questions. I'm guessing two. Like a 25-minute and a 12-minute. They're usually the way they break them up.
Mm.
I think they're only giving you like an hour. Is it an hour? I can't remember now. Might only be 45 minutes even. They're also going to send me your responses, which is the first time they've ever done that. So please don't write on there, you know, something derogatory towards me and blame me, because I'll read it. Or if you want, go ahead, it's fine. All right. Initially at rest and free to move without friction on an XY
Why
plane.
wouldn't it be D?
I don't know. I haven't read the question yet. Constant net force of magnitude F is directed in the X direction for 1 second.
What's K?
All right. So, which of the graphs represents the kinetic energy? So, kinetic energy doesn't care about direction. So, force, so it would have, and the question is they act for 1 second each. But since it acts in like the first one, you apply a force on an object for a second, it's going to move a certain distance, right? If it starts from rest, correct?
Yeah.
Well, when you apply, even though it's moving in the X, when the Y force applies, is it moving in the Y? And it's not. So that's, so as far as the Y force is concerned, the thing is starting from rest. The fact that it's going left and right doesn't matter. So you can argue that it's going to, the forces are going to be applied for the same amount of distance. So I would say is it going to be a linear increase, force, constant force, time?
Wait, so what were you talking about, the X and Y again?
So first of all, I would say the answer is, I think the answer is going to be D.
That's what I thought it was, but it's B.
What do they say it is, B?
Mm-hmm.
All right, so then kinetic energy, time, force. All right, so the reason they look the same, first of all, is because the situation is the same in for each of them. If when it starts, oh boy, the object in question, sitting here at the origin, doesn't have any velocity at all, right?
Mm-hmm.
Force is applied to it for 1 second. Okay, that's why. Okay, so the kinetic energy, by the way, the shape of these is because applying a force is going to apply a constant acceleration, which is going to change the velocity at a constant rate. But kinetic energy is 1/2 mv squared. So as this velocity changes, the kinetic energy increases as a squared. That's why they're shaped like this. Now, my point is the object is moving later on in the X direction. Jesus, this is horrible. I'm going to try arrows. Okay, I said arrows. Okay, just a nightmare scenario. Purple, I'll take purple, that's fine. Okay, except I want an arrow. Except you're not going to give it to me because it's, yeah, okay. You bastards. I got it. There we go, that'll work. So the velocity is horizontal. Well, the force is vertical. So what's the initial, as far as the force is concerned, what's the initial velocity of the object?
0.
0, because it doesn't have a vertical component to its velocity. So it behaves, it will apply it over that same force over the same distance. If you apply the same force here to the object horizontally, when it's already moving, you're actually going to apply that force over a larger distance because it's going to be moving farther. which is a little bit of evidence in the sense that speeding your car up is, you require more energy to do it from, say, 60 miles an hour to 80 than you do from, say, 20 to 40. Even though the change in velocity is the same, the squaring makes it actually harder to speed it up. You have to put in more energy to speed something up that's already going fast. So yeah, that's why these are the exact same shape, because the velocity, the initial velocity in both cases is 0. Even though this one is the second case is moving, it's moving horizontally. So as far as y is concerned, its initial velocity is 0.
What would it look like if both cases were in the x?
It would, well, if you applied the same force, it would just be a continuation of this. You would basically just get this parabola continued, more curved.
Would it look like A or C?
It would look like A in the sense that it would be a parabola. Consistently, yeah. I mean, it may be A. A would be the closest thing to it. If the force, basically, but you would apply the same force. You would just continue applying the same force if you switch the direction. So, not switched them, but if you made it just only act in the x. I don't know what the heck this is. This, because the kinetic energy's got the squared in there, there's no way this is like a square root or something. This curve makes no sense whatsoever. This is if you forget it, it's a squared it completely and you just treat it like a line. That's what I did the first time. This shows no increase for the first second. It shows that it was already at a kinetic energy, which we know it wasn't. It started at rest. So there's no way it could have started with the kinetic energy. That one should have been easily ruled out. This one's dangerous because, like I said, if you forget the kinetic energy, got that v squared in it, and you don't look at it that way. All right. Now, we have, there's the multiple choice 2. I've given the answers are both posted up there, and then after that, we're looking at, I don't think you can see this. Let me see if I can get into this.
Oh yeah, are we gonna have a marking period 3 test?
I don't have time to waste to get you guys ready for the exam. I do not have time to waste giving a test. So, I haven't given much thought to it yet. I'll probably have to end up giving everybody a decent grade. Grades in general for this class are going to be a real treat to try to figure out. I really don't know what I'm going to do yet with it. I'm looking for this folder. There we go. No, that's not it. There it is. All right, so let me change this. And all right. So yeah, I have really grades. I have no idea. Have you asked your teachers yet about grades? Have you hammered them on them yet, Alex? Is this all going to count? What's our grade going to be? You should really do that as much as you can. Yes, ma'am. What class did you guys have today?
English.
Math.
Who do you have for math?
English and math.
Who do you guys have for math?
Collins.
Who do you have?
Collins,
Alex?
Collins, we're in the same class.
No, you're in the same. You have the same two classes together.
Not
No, I have been.
English.
All right. So, So, out of these, have you done? You should have. I think we've looked at most of these, haven't we? Yes. No. Some of the ones later are definitely like these guys. I don't know if you guys have looked at these yet or not, but they're ones I find pretty good for understanding things. And the addendum, there's an addendum, isn't there?
Yeah.
There it is. The addendum's good because it's got springs involved. That's why I put it in there.
What's an addendum?
Anything that you add on.
Oh.
So, yeah. Yeah, if you just add on something like an amendment, it's a very similar word. Addendum's more of a not really a change in, but something in addition to. Makes you sound like you know Latin and stuff like that. So, if you like, I would suggest working on those. I'll give you a couple minutes. And by the way, if you have everything you need, you don't have to sit here in awkwardness. You can just, you can just log out and I'll be like, oh, they left. Not a big deal. I'm not, this is a help session, not like you just cut my class. Alex, you changed camera angles more times than I've changed underwear this week. I mean, my God.
I'm using a phone, so I have to bring it close to me to see it.
Is that better? All right. So when we do the testing, one of the things we're gonna have to do is make sure everybody has an actual computer. You could do it on your phone, they say. Seems to me that would be difficult, but you can take pictures of your responses and send and upload them. I think I would rather do that if I was doing physics, just because equations and so forth would seem like to be a pain if I wanted to use them by typing. Let me pull this up. There we go. All right. So which one of these is 0? Both before and after.
Is that one of the pictures online? I mean, problems.
Oh, well, what?
Was that in typers?
Yeah, it's in the addendum. You can see my screen, right?
Yeah.
All right. Out of kinetic energy, potential energy, gravitational, and potential energy spring, which one of them is 0 at the beginning and 0 at the end?
Out of
Gravitation?
Right, because does it go higher?
No.
No. So right away, what we're seeing, hold on. Get you guys out of the way, and here you go. So one of the things we're seeing right at the start here is it doesn't change height. So our gravitational potential energy is, this is 0 here, and it's 0 here. I swear. Okay. I got this. There we go. Okay. All right. Is the box moving at the beginning?
No.
So what's that tell us?
Initial K 0.
All right, good.
Yeah.
All right, initial kinetic energy must be 0.
And it
Alright.
says the string's unstretched, so it has an initial potential spring energy of 0.
All right, I'll buy that as well.
Are you just supposed to write numbers on the dashed lines?
What, write numbers here?
Yeah.
No. You don't have to. I mean, if I drew a block, I might. You could write just, 0 for each. 0 joules there, 0 joules.
But I mean, like, if it was like a test and we were given this, are we supposed to write
They would
numbers,
they want the bars. They say label the column heights. So yeah, I guess they want us to give them a number. So what about work done by external forces?
60 newtons.
Close.
Oh no, it's
60's involved, right?
yeah, but it's still work done. How do you know the distance? Oh, it's 2 meters, so it's 30 newtons.
Force times distance.
Oh, times distance. It's 120.
120. All right, so we know that this now represents 120. I just decided. Joules. So the external force, the hand that pulls it, put in 120 joules of work. So how much is in spring potential energy and how much is in kinetic energy? Do we have enough information to figure at least one of those out? Because we need at least one of them.
Which ones were they again?
Well, we got kinetic energy and spring potential energy. So we know kinetic energy, for example, 1/2 mv squared. I could figure out m because I know the weight of the box.
Mm-hmm.
Do I have any indication of what the velocity is?
No.
Yeah, so I'm thinking I don't have that. What about spring potential energy? Alex is the one that I had to send you earlier. All right.
Oh, yeah, it's U equals 1/2
K distance stretched squared. Do I have enough information to find this out?
Yeah.
Do I have the K? Yes. Up here. Let's use the highlighter tool. I have the K. And I have the distance. So I should be able to find the spring potential energy. And then what will I do? How much kinetic energy is it going to have then?
the same as the potential energy?
I wouldn't say the same
Oh.
necessarily.
Oh,
How much energy was
it
put into
has
this?
to, yeah, it has to add up to the rest of it.
There you go. So I put one, there was nothing in the beginning. I added 120. So one thing I know is that whatever this block is and whatever this one are, they've got to add up to 120. So these little buggers are helpful for understanding the whole process. All right. Here's my suggestion. Without any additional questions from your end, I don't want to give away too many things. I want you guys to work on this, and I'd rather you text me later on today with a question than to sit here and continue to do your homework for you, which I know you're not mooching, but you know what I mean. So I would start with those typers. I would start with the addendum and no, where are they? And the end of the other ones. So I think they're actually in here. Yeah. There we go. So and the later ones on this one in particular, the ones with the bar chart thingies. So starting in here, like 19, 20, they're not bad to look at. But then the addendums, and then finish up those multiple choice. Feel free, shoot me a text, and I'll post a solution or give you an answer or explanation. All right.
Okay.
Yeah.
All right. No more point in just watching me eat popcorn. That's not fun. All right, guys. I'm gonna end this one. Anybody that shows up this late to a help session deserves to not have me not be there. All right. See you guys.
See ya.
Yeah.
I can't go. I'm that close. I got my own damn meeting. Here we go. How do I make this bigger? Alex, I'm stuck. I can't make my. I don't want to hide it. I want to make it bigger. Oh, wait, I know what it is. I got it. I figured it out. There we go. Okay. Now I can do it. See ya.